All right, so suppose that we've got a sequence of positive numbers, and we look at the sequence of partial sums of that sequence. So Sn is the sum of the first n terms in this sequence. And let's suppose, furthermore, that the series, this sequence, diverges. All right, and now what I want to consider is a tail of a new series. Okay? And this one is going to consist of the terms in this sequence divided by the partial sums. All right, so this is going to be a much smaller, a sum of a bunch of much smaller numbers than our original series. Okay, so I can write out this tail like that. Now, because the sequence A consists of all positive numbers, the sequence S is monotonic increasing. All right, so here I'm dividing by Sn plus 1. Here I'm dividing by Sn plus 2. And here at the end, I'm dividing by the biggest of them, Sn plus P. Now, what I'm going to do is say, well, geez, this is clearly bigger than what it would have been had I divided by n plus p the whole time. So this would be an plus 1 over Sn plus p plus an plus 2 over Sn plus p plus all the way up to an plus p divided by Sn plus p. Now, here they all have the same denominator. So that means that I can just add the numerators up. All right, and so I'll get an plus 1 plus an plus 2 plus all the way up to an plus p, all divided by Sn plus p. Now, this term here, this sum, is a tail of the S series. All right? Sn plus p is equal to the sum of all the a's from 1 to n plus p. But here, I'm only starting at n plus 1 to n plus p. So the terms that I don't have are from 1 to n. And of course, that's just S sub capital N. So this numerator is just S n plus p minus Sn divided by Sn plus p. And then I can split the numerator, and I'll view this. This is equal to 1 minus Sn divided by Sn plus p. Now, if I allow p to grow without bound, then the denominator here will grow to infinity. And that's because we assumed that the series diverged. All right? So down here, remember, capital N is fixed. It might be very, very, very large, but it's constant. P is not fixed. The statement of convergence was that we had to be able to add any number of terms we wanted past capital N. So I can let P grow without bound. This will be fixed. That will grow without bound. And that makes this term that I'm subtracting from 1 go to 0. So this ratio tends, as p tends to infinity, to 1. And that means that I certainly cannot make it less than any epsilon greater than 0. Okay? Because it tends to 1. So that implies that this series also diverges. I'm taking the terms that I originally added and I'm dividing each one of them by something that's going to diverge. It's going to go to infinity. So I'm dividing by a bigger and bigger and bigger number. But we find when we add them all up that that's not enough to get us to converge. The series still diverges. To see how truly earth-shattering that statement is, let's consider an example. All right, suppose that AK is equal to 1. For all K. So then Sn would be the sum from K equals 1 to N of 1, which is just N. Okay? And obviously, that diverges. All right, if you just keep on adding up 1, you're going to get a divergent series. So now what we just showed is that that implies is that the harmonic series diverges. All right, so the simple divergence of 1 plus 1 plus 1 plus 1 plus 1 plus dot, 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 dot is, from this perspective, enough for us to conclude that the harmonic series also diverges, even though that one's not as obvious. All right, we'll find later on that this series, the harmonic series, behaves like the natural logarithm. All right? So the sequence of partial sums of 1 over k behaves like a natural logarithm. So the divergence of the harmonic series will then imply the divergence of this new series. All right. And then, of course, we could take partial sums of this series and divide by that. And we would get another series that diverges. Each of these series diverges at a slower rate, in fact, an exponentially slower rate than the one used to get that series. But despite that fact, even though they diverge slower and slower and slower, they all diverge. So that indicates that there is no slowest diverging series. If you give me a series that diverges, I can construct one from that series that diverges even slower.